So the next 2 days, I'm going to be out during class for Thursday and Friday for laptop training for the district. And you guys are going to be exploring section 11.5, which is lines and planes in space. Now this is huge for you guys. It's basically a 3D version of geometry as we deal with lines and planes and how we can start using them and applying them in the Calculus 3 perspective. But before you do that, you have a mini quiz on the dot product and cross product, which we'll be using heavily in the next couple days. So take out a sheet of paper. It's only 2 questions. One on dot, one on cross. You don't know which one's which. Should be pretty straightforward. When you do finish it, just turn it into the sub, and then we can continue on with the video lecture. So here are the 2 questions. I'll have one of you pause the video and take, 10 minutes, 15 minutes at the most to finish these 2 questions. Pause the video again to complete it. Once everyone is done, we can resume the lecture. So as I mentioned before, earlier, that we're doing not 10.5, we're actually doing 11.5. 10.5 was the old book from last year. So 11.5, lines and planes in 3D. In geometry, a couple years ago for you guys, lines in 2D were all about slope, but in 3D, it's all about vector. So slopes give you a rise over a run. Well, in 3D, it's hard to determine a rise and a run because it's almost like there's a rise, that was the change in y. There's a run, which is a change in x, but what's the change in z? So instead of trying to come up with a 3D version of slope, we're going to come up with it in terms of vectors. So I'm going to draw a picture so you guys can kind of see how this can look in terms of vectors. So we got our 3D world. I'll draw a vector, and let's just put it right there. And we'll call that vector v, and the orientation of it is A, B, C. Okay? So when we talk about lines in the 3D world, let's say I put a line there. Now, everything about the line is going to be parallel to a specific vector. So that blue guy is going to be parallel to the green guy. And the one extra thing that you need is, where am I going to put that guy? It all depends on a specific point. So if I have a point and a vector, I can put my line through that point and make it parallel to the vector, and there we go. Now, let's label the point. This is the specific point, and we'll call that point, let's go x naught, y naught, z naught. Okay? And we know that any other point on the line, we'll call this x, y, z. So I can create a vector from the given point to any point on the line, and that vector would be x minus x naught, y minus y naught, z minus z naught. Now, that red vector has to be, since it's on the line, and I already told you the line is parallel to the green vector, how do we write an equation relating the red vector and the green vector discussing parallel? Now remember, slopes in geometry, parallel means you have the same slope. Well, in vector world, which we are in for 3D, there is no such thing as slope that we're focused on. We're focused on the directions of vectors. So a little reminder about being parallel is the red guy is going to be the equivalent of the green guy with a scalar multiple of it. So t dot v, and that t is a scalar multiple multiple of v. That makes it parallel. Okay. So just number-wise, you can talk about being, so for an example, is 2, 4, 6 parallel to 1, 2, 3. So I go right 2 on the x, up 4 on the y, and up 6 on the z, or however you want to say it. 2 positive right, or sorry, 2 positive x, 4 positive y, 6 positive z. Is that the same directional units as going 1 positive x, 2 positive y, and 3 positive z? And you would say, yeah, because what you could say is 2, 4, 6 is a scalar multiple of 2 times that 1, 2, 3. So since that is a scalar multiple equals parallel vectors. So let's start coming up. So with that in mind, let's kind of use the fact that this red vector, let me highlight this part again, the red vector, which came from the line itself, has to be parallel to a specific given vector, which was the green guy. So if I want to expand on that, then I can say that x minus x naught, y minus y naught, z minus z naught needs to be the equivalent of t, comma, or t dot, instead of just the vector v, let's put it in its components, a, b, c. Okay. So, in looking at this and just focusing on each section, you could say x minus x naught equals at. Then you could say y minus y naught equals bt. And the last component is z minus z naught equals ct. Okay? So, in that form, there's 2 ways to write an equation of a line in calculus. The 2 ways are you can solve for each variable x, y, and z. Because remember, those are the variables. X naught, y naught, and z naught are a specific point, and t is just a scalar multiple. It's just a number. Okay? So you can do that, or you can eliminate the t scalar parameter and you'd have another version of the same line. So the parametric equation of lines is x equals x naught plus at, y equals y naught plus bt, and z equals z naught plus ct. If you notice, this is my form 1 right there. All I did was I solved for each of the x, y, and z. So the point is x naught, y naught, z naught, which is on the line, and it's guaranteed to be parallel to the vector a, b, c. Now the other way is not parametric, but it's called the symmetric equations of lines, which is basically eliminating the t by solving for it. And you can get x minus x naught all over a equals y minus y naught all over b, and z minus z naught all over c. So this would be the second version of writing the equation of line. That's similar to geometry. Y equals mx plus b. That's the slope-intercept form. There's the point-slope form, y minus y naught equals m times x minus x naught. And then there's that general form, ax plus by equals c. All the same line, just different ways to write it. So with that in mind, lines, let's look at an example. It says, find the equation of the line through the point 1, 2, 3 and parallel to the vector 4, negative 3, and 5. This is pretty straightforward because you already have the point and you already have the parallel vector, so you can just write them right in. So the parametric way would be x equals x naught plus at, which would then be 1 plus 4t. The y would be y naught plus bt, so the y would be 2 minus 3t. And the z is z naught plus ct, so z would be 3 plus 5t. So that's the parametric way. Now notice, I am giving you a specific point, but there are many points on a line, infinite amount of points. So I could give you another point on the line. And to get any other point on the line, just use a different t. Right now, if you plug in t equals 0, it gets you the 1, 2, 3, because it's your initial point. So let's now use t equals 1. And let's just look at what your next point could be. Your next point here would be x would be 5. Y would be 2 minus 3 times 1, which is negative 1. And z would be 3 plus 5, which is 8. So if I want, I could use the point 5, negative 1, 8, and I could create a whole new set of equations for the same line. I could say 5 plus 4t, y equals negative 1 minus 3t, and z equals 8 plus 5t. Okay? So kind of the moral of this would be you can use any point on the line as long as you use the same vector. Therefore, many ways to write same line. If you're not used to it, the 3 dots like that, that means therefore. Okay? So that's kind of lines in general. Today we're doing 2 things, lines and planes. But before we get to the planes part, I have 2 examples about lines. Okay? So in 27 through 30, this is from the old textbook. It says, determine whether the lines intersect, and if so, find the point of intersection and the cosine of the angle of the intersection. So let's just look at number 28 first. We're going to do 28 on this slide. We'll try 30 on the next slide. Okay? So 28, let's kind of look at this. Let's kind of extract some things. So using this guy, the very top one, we can have a point. The point would be 1, 1, 4. This is knowing it from the parametric equations. And the vector, let's call that vector v, is saying the direction of my line is negative 3, 4, 2. Okay? And we can also look at this vector, which has a point, 1, 4, 1. And it also has a direction, I'll just call this one u for now, of 3, 2, negative 1. Notice that that second vector, the blue guy, is in terms of s's. Remember, that s or t is just a scalar parameter. It can be whatever it wants. It's just reminding you that it's a multiple to make it parallel. So I have the 2 points and the U and the V. Now, in 3D world, it's a little bit harder to tell if things intersect or not. Because I could say, here is that line, but remember, this is in 3D, and I'm drawing it in 2D, so it's kind of hard to see. And let's say this is the other line. Okay? Well, in 2D world, you intersect if you're not parallel. But that's where the issue is in 3D, is remember the word skew? That's a geometry term using a three-dimensional idea of skew. Right now, this green line and blue line, if I extended them in 2D, they intersect. They definitely intersect in 2D right there. But in 3D, that blue line could be lower than the green line. Think about planes flying in the sky, and they would not hit. A good visual for it is, if you remember, looking at a cube, I could say this is my green line, and this is my blue line. You cannot say they're parallel because they're not in the same plane. They're not in 2D world. So they're not parallel, but they do not intersect because the green line will always be above it. But if that blue floated up to here, they do intersect at that top left corner. So it's a little bit harder in 3D world to determine if they hit or not. You can't just look and go, oh, since the vectors are different, then they must hit. Because the vectors can be different, but again, they can be skew. So here's what we're going to do. We're going to see if we can get the intersection by setting the x's, y's, and z's equal. So to find potential intersection, we're going to set x's equal, y's equal, z's equal. Okay? So, when I look into this, look at the x's, and my x's were negative 3t plus 1 equals 3s plus 1. So if I want to solve this as much as I can get negative 3t equals 3s, so t equals negative s, or s equals negative t. Okay, there's my x's. Let's look at the y's now. So the y's would be 4t plus 1 equals 2s plus 4. And we just said that t is negative s, so I'm going to plug that in here. So I got negative 4s plus 1 equals 2s plus 4. So I got 3 equals 6s, so s equals negative a half, which therefore would mean that t equals a positive half. Okay? Now, this is a 3-equation system, x's, y's, and z's, but how many variables do we have? 2, the t and the s. So just because I solved and I got an s and a t, that does not mean this actually works. So those are my x's, those are my y's. I'm going to actually need to look at my z's as well. So if I come over here and I look at the z's, it has 2t plus 4 equals negative s plus 1. Well, let's plug in the things that we know. That's 2 times 1/2 plus 4 equals negative a half plus 1. And I get 5 does not equal 1.5. So the t's and s's, I solved for them, and they gave me answers that satisfied the x's and the y's, but not the z's. So since this is not true, there is no intersection. In other words, lines are skew. Okay? They do not intersect, but they're not parallel. They just do not intersect. Okay? So, I want us to try number 30 out now. I'm going to see if we can get 30 and see if it intersects or not. Now this time, if you notice, this is in the symmetric form, okay? Because it's this guy equals this guy, which equals this guy. So let's call the parameter here on this piece, let's call these the t parameter. And over here, let's say each one of these is set equal to an s parameter. You do not want to say they're equal to the same t parameter, because remember, that's just a scalar multiple. So we're going to try this one out. Okay, let me check the time on the recorder first. Okay, I'm going to stop here, and we're going to start up again on the next video.